Vibration testing is a critical process used to evaluate how a product or component performs under real-world vibrational conditions. It simulates the mechanical stresses and motions that an object may experience during transportation, operation, or environmental exposure. The purpose is to identify potential failures, ensure structural integrity, and improve durability. It involves placing the device under test, DUT, on a vibration shaker, which generates precise motion, typically sinusoidal, random, or shock, to mimic real-world stresses like transport, operation, or environmental conditions. Let's take a moment to understand why vibration testing is so crucial across industries. This slide highlights why vibration testing is essential across industries. It validates durability under real-world conditions like transport and operation, ensures reliable and safe performance, preventing unexpected failures, helps meet global standards like AIS 156, UN 38.3, ISO, and SAE. Detects design issues early, such as loose joints, weak welds, or material fatigue. Prevents failures like fire, leakage, or connector disconnection. Reduces warranty claims and costly recalls. Aids in design improvement and product optimization. It's critical for automotive, aerospace, electronics, and battery sectors. In short, vibration testing ensures our products are safe, reliable, and compliant. Let's quickly go over the main types of vibration tests. Sinusoidal. This one's single frequency and control, mainly used to find resonance points. Random. Simulates real-life road or field conditions, more realistic than sine. Mixed mode. A combo of both, useful when you have both steady and unpredictable vibrations. Shock drop. Short, sharp hits. Checks how well a part can survive drops or sudden impacts. Combined environmental. Adds temperature or humidity while vibrating. Tests how things hold up under multiple stresses at once. So, depending on what we want to check, we use one or a mix of these. So this is the Indian standard for EV battery vibration testing. The main goal here is to make sure the battery stays safe during transport and regular vehicle use. As you can see in the slide, the test uses a sinusoidal sweep from 7 to 200 hertz and back, repeated over 3 hours total. The test is usually done along the vertical axis, but can be changed according to the orientation of use. And the battery should show no damage, leakage, fire, or explosion after the test. It also needs to work properly post-test, no exceptions. You can also see the setup and the acceleration versus frequency graph on the right. UN 38.3. This test is quite similar to AIS 156. Both use a sinusoidal sweep from 7 to 200 hertz. But here, the key difference is UN 38.3 tests in all three directions, X, Y, and Z, not just one. That's because it's meant for global transport safety of lithium batteries. As shown, it runs 15 minutes per sweep, 12 sweeps per axis, which totals to a 9-hour test across all axes. The battery should show no leakage, rupture, fire, or disassembly, and the voltage drop can't exceed 10% from the start value. You can also see the frequency versus acceleration plots for each axis in the slide. This standard focuses more on how battery packs handle both electrical and mechanical stress, especially in real-world EV conditions. It follows a random vibration profile based on IEC 6068-2-64, which is different from the sinusoidal sweeps we saw earlier. What makes this unique is that it can also be tested under extreme temperatures, from negative 40 degrees Celsius to plus 75 degrees Celsius to simulate harsh environments. The battery must show no structural damage, and after the test, its capacity and insulation resistance should stay within acceptable limits. You can see the setup and random vibration test plot on the right. SAE J1455 standard. This one's focused on commercial and heavy vehicles like trucks, buses, and off-road machines. The test uses both random vibrations and shock pulses since these vehicles face rougher conditions. The vibration profile changes based on where the part is installed, like on the chassis, axle, or inside the cabin. It's also common to combine it with thermal or humidity stress to see how electronics perform under extreme real-world conditions. Passing means the device must still function electrically with no connector issues or physical damage. You can see a basic test setup and the general vibration profile at the bottom. ISO 16750-3 Random Vibration Test. Imagine you're driving down a rough, bumpy road. The kind of vibrations that shake your vehicle are exactly what this test simulates. This test checks how long a battery or electronic unit can survive random vibrations, not the clean, repeating kind, but the chaotic, real-world ones caused by poor roads. The main issue we're looking for is fatigue failure, tiny cracks or damage from repeated shaking over time. In this test, the product is mounted just like it would be in an actual vehicle. Same orientation, same frame, to make sure the conditions are realistic. The standard defines PSD values across different frequencies as shown in the table, and the test maintains an RMS acceleration of 27.1 meters per second squared. As for passing, it's simple. No breakage, and the device must function as per ISO 16750-1, Class A, meaning it must work properly during the test. So, in short, this test tells us if a product can handle rough rides without giving up. USCAR standards. This one is all about testing connectors, sensors, and modules in cars to make sure they're reliable. The test uses mixed mode vibration, so that's random plus mechanical shocks. The exact vibration profile depends on where the part is used, like under the hood or inside the cabin. To pass, there should be no loosening, disconnection, or structural issues, and the electrical contact resistance must stay stable. You can see a bulk connector test set up in the image. This slide is here to show the core international standards that form the foundation for most vibration testing methods. Each standard focuses on a different type of vibration. 60068-2-6 handles sinusoidal tests, useful for resonance and fatigue detection. 60068-2-64 deals with random vibration, which is great for road and transport simulation. 60068-2-80 combines both, called mixed mode testing. These standards are referenced in all major vibration testing protocols like AIS 156, ISO 12405, UN 38.3, and ISO 16750. So, understanding this series helps connect everything across different regulations. At November Services, we offer end-to-end vibration testing solutions, covering all major types like sinusoidal, random, mixed mode, and shock testing, following standards such as AIS 156, ISO 12405, UN 38.3, and more. We're not just a test lab. We also provide consultancy, engineering support, and product development insights to help you improve design and ensure compliance. Our advanced facilities serve industries like automotive, aerospace, electronics, and energy storage, ensuring your product is validated, reliable, and ready for the real world. Thank you. Thank you for your time and attention. If you'd like to know more or need guidance on any testing and related standards, feel free to contact us directly. Let's stay connected for more industry-level insights, testing knowledge, and technical updates. Stay tuned, and let's build better, more reliable products together.